welcome back. In this lesson, we're going to look at rounding and estimation. So what's the difference between estimation and rounding? Well, rounding is actually a type of estimation. Estimation is just a process of arriving at an approximate answer to a question. In the real world, be, let's say, you think of someone's age, right? Normally, you're not exactly that age. So, for instance, if I was really 20 years old and 5 months, I am more than likely not going to tell someone that I'm 20 years old and 5 months, right? I would probably round that to about 20 years old. So that's an approximation for my age. And that symbol there is the symbol for approximately equal to. So you'll be seeing that quite a bit. A lot of times we need to round whole numbers for one reason or another. It's a very useful skill when we're trying to estimate. So what are whole numbers, first of all? Well, you have the counting numbers or natural numbers plus the number 0, okay? So the natural numbers or counting numbers start at 1, and they include all the positive natural numbers to infinity, okay? If I take the number 0 and add that onto the natural numbers, you get the whole numbers. So whole numbers are 0 plus all the natural numbers, and so on. Okay, so how do I round those? If we take a number like this, okay, each of the digits, so these are digits, is in a specific place value. So when we start to the right, we are in the ones place. And then as we move to the left, we add a 0. So if I add a 0 to 1, I get 10. So this is in the tens place. And then this is in the hundreds place. And then you have the thousands, 10,000s, 100,000, million, 10 million, 100 million, billion, and so on. Okay, so since the first number to the left is in the billions place, I would read this 7,843,169,634. If you take a number that has a decimal point, like pi, we know the approximate calculation for pi is 3.14, right? That's what we're used to. But it goes on forever. It's an irrational number. It's non-terminating and it's non-repeating. So an even better approximation for pi is 3.141592. And you have this decimal point here. So this number here is the equivalent of the 4 in this number, okay? Because I can put a decimal point at the end of this and add a bunch of zeros and it wouldn't matter, okay? So here, the 3 is in the same spot as the 4. It's in the ones place. As we move to the right past the decimal, now we have the tenths place. So now it's like we're dividing by 10 each time. So I've got 1/10, and then the hundredths, and then thousandths, 10,000ths, 100,000ths, and millionths place. So when I want to round those numbers, because as you can see, you have some pretty large numbers or long numbers, sometimes it doesn't make sense to write out every single digit. We just want an approximation, so we round it. So when you're rounding whole numbers, you look at the digit to the right of the digit where the rounding is to occur. Okay, so let's say I was rounding the number 634 to the tens place. That means I'm going to look to the number to the right of it, and that number is going to tell me what I need to do with the 3. If the digit to the right is 5 or greater, you add 1 to the digit to be rounded. So you go up 1. And you replace all the digits to the right with zeros. If the digit to the right is less than 5, you don't change the digit to be rounded. You just leave it the same, and you replace all the digits to the right with zeros. So for example, if we take this number here, which actually is the world population, right, a rough estimation, and we want to round it to the nearest 100 million. So you can use your chart. The 100 million place is where the 8 is. Okay, so again, you have ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. So I need to look at the 8, okay? I'm going to look at the number to the right of it. So that means I'm going to look at the 4. Since it's less than 5, I'm just going to leave it a 4, and I'm going to replace all the other digits to the right with zeros. So I'm going to just write down the 7 and the 8, and then remember all the other digits are going to turn to zeros. So that's how we would round the world population to the nearest 100 million. If I went around to the nearest million, okay, I need to figure out where the millions place is. And that's where the 3 is, okay? So that means I need to look at the right, and that 1 tells me again, since it's less than 5, I'm going to leave the 3 the same. So I'm going to have 7, 8, 4, 3, and then I'm going to turn the rest into zeros. And again, if I went around to the nearest 100,000, okay, I need to look at the 1 here. Okay, that's in the 100,000 place. So that means if I look to the right of it, the 6, that is greater than 5. So I need to, and actually I should say it's 5 or more, right? Because if that was a 5, I would also round up. So that means I need to round this 1 to a 2. So it's going to be 7, 8, 4, 3, 2, and then the rest are going to be zeros. Okay, in this example, we're going to look at rounding when we have a decimal point. So like the number pi. Let's say I want to round to the nearest hundredth. So I need to figure out where the 100th place is. Remember, this is the ones, and then you've got the tenths, the hundredths. So because that 4 is in the 100th place, I look to the number to the right. And remember, if it's less than 5, you are just going to keep that the same. So it's 3.14. Now, it says to replace all the other digits with zeros, but those zeros are insignificant, right? They don't affect anything, they don't matter. So we can just leave it as 3.14. So the rules slightly change when we have a decimal point. Okay, don't worry about those extra zeros there at the end of the number. All right, if I went around to the nearest thousandth now, so again, this is the tenths, hundredths, thousandths. If I look to the right, that's a 5. 5 or more, you round this number up. So that 1 is going to turn into a 2. So it's going to be 3.142. And again, I don't need to worry about the zeros at the end. Now you can pause the video and try the 2 check your understandings, and then unpause when you want to go over it. Okay, so we need to round the world population to the nearest billion, and the billions place, remember, is where the 7 is. So if I look to the right of it, that tells me I need to round this up to an 8 because it's 5 or more. So that's going to turn to an 8, and then I have 9 zeros that follow it. So it's about 8 billion. If I went around to the nearest 10 million, okay, here's your world population. Nearest 10 million would be the 4. If I look to the right, that's less than 5, so we're just going to keep that the same. So it's going to be 784, and then we're just going to fill in zeros. For the check your understanding number 2, we have the number pi. We went around to the nearest 10th. So you've got this number here is in the 10th spot, the 1. The 4 tells us to keep it the same, so it's just going to be 3.1. Remember, we don't have to worry about the zeros because of the decimal point. And then to the nearest 10,000th, right? You're going to go back, and 10,000th is the 5. The 9 tells us to make that a 6. So it's going to be 3.1416. Let's look at another example, and we can see where this would be useful. You purchase bread for $2.59, detergent for $5.17, a sandwich for $3.65, an apple for 47 cents, and a coffee for $8.79. The total bill given was $24.67. Is this amount reasonable? So if you're out, with friends or yourself and you're buying something and you receive the check, it's always good to look at it and approximate, whether that total is roughly what you should be paying, okay, because mistakes can be made. So I'm going to take each of these prices and I'm going to round them, okay, I'm going to estimate them. So $2.59, we can round that to about $3, right, because if I want to round to the nearest dollar, I'm going to look at the 5, because this is your cents, that's your dollars, so that 5 tells me I'm going to round that up to a 3. Okay, so that's about $3. For the detergent, $5.17. We'll round to about $5 because the 1 is telling me to keep the 5 the same. Okay, and then you've got $3.65, which is about $4. And the 47 cents, that would round to basically $0. Okay, if we're rounding to dollars, cents, you could round it to about 50 cents. And then $8.79 would round to about $9. Okay, and I would just add that up really quick. So 3 plus 5 is 8, plus 4 is 12, plus 9 is 21. So I'm getting $21, okay? And the total bill given was $24.67. So the total bill seems a little high. That's something you would definitely want to check before you were paying. Okay. You can try the next one on your own. And the next one has 2 parts to it. And you can unpause the video when you're ready to go over it. So this problem is very similar to the one we just did. You and a friend ate lunch, and the check for the meal showed soup for $3.40, etc. You want to round the cost of each item to the nearest dollar and obtain an estimate for the food bill. Okay, so you've got $3.40 for the soup. So if we round that, that's going to be about $3. And then I've got $2.25. That's going to round to $2. $5.60 would round to about $6. $5.40 would round to $5. $3.40 would round to $3. $2.85 would also round to 3, and then chocolate cake would round to 4. And if I add those, 3 plus 2 is 5, plus 6, 11, plus 5 is 16, plus 3 is 19, plus 3 is 22, plus 4 is 26. So I'm getting about $26. Okay, so that's about what the bill should be. And it tells us that the total bill before tax was given as $29.85. So do you think this is reasonable? And again, we're getting a rough estimate of $26. That was before tax. Even the bill being $29.85 seems a bit high. Okay, let's look at another example where we have to use some math skills and also some rounding and estimation. So a carpenter who works full-time earns $28 per hour. Estimate the carpenter's weekly salary. Okay, so we're estimating, right? So $28, we can pretty much round that to about $30. So $28 is approximately $30. And we are going to assume here, like in a week, right? Normally a typical work week would be 40 hours, right? 8 hours, 5 days. So that gives us 40 hours per week. So if I want to figure out the weekly salary, we know that they make about $30 per hour. So $30 for every 1 hour. And I'm going to multiply that by 40 hours per week. And you're going to see this skill later in the unit. We're going to look at dimensional analysis. And it's a certain way that we can work with different dimensions to end up with the dimension that we want. So here, since we're looking for a salary, we know we want to end up with money, right? In this case, dollars. And we're looking for weekly salary. So we want money in terms of the week. So here, I can cancel out the hours, and I'm left with 30 times 40, which is just $1,200. And then I'm also left with weeks. So the carpenter makes about $1,200 a week. Now, if I want to estimate the annual salary now, right? Annual means yearly. I know that there's that the carpenter makes $1,200 a week. And how many weeks are in a year? There's about 52 weeks in a year, but we'll round that down to about 50 weeks. Okay, so I've got 50 weeks per 1 year. And we know that the carpenter makes $1,200 every 1 week. So I can cancel the weeks out. They're diagonal from each other. They would simplify to just 1. Week divided by week is 1. And then 50 times 1,200 gives me 60,000. So it's about $60,000 per year. And again, that's an estimation. You can try the next one on your own and then unpause the video when you're ready to go over it. In this next example here, the check your understanding number 4, it's solved very similar to the example we did. So here, the difference is that it's a landscape architect who works full-time and earns $52 per hour. Okay, so again, we can round $52 to about $50 to make it easy for us. And we want to look for the weekly salary, right? So it's $50 per hour, so over 1 hour, times, again, we figure there's about 40 hours in the work week. So 40 hours per 1 week. And we can cancel the hours out, and 40 times 50 leaves us with $2,000, so it's about $2,000 per week. And we're looking for the annual salary, so as we talked about in the last example, There's 52 weeks in the year, but we can round that to about 50 weeks in 1 year. And then we're going to multiply that by $2,000 per 1 week. And now we're left with the amount per year, right? So 50 times 2,000 gives us $100,000 per year. Some of the things that we're going to look at in this course are going to relate to graphs, and sometimes it's helpful to look at a graph and make estimations because we can't always tell exact things from graphs for many reasons. So what we have here is what's called a line graph, okay? And line graphs are used to illustrate trends over time. When I say trends, I mean like increasing and decreasing, different patterns. And if you take a look at the line graph here, okay, the title is The Probability of Divorce by Educational Attainment. And you've got the red line graph showing us high school and no college. So that means that the couples, their highest degree was a high school degree. They did not go to college. And then the blue is showing us the couples who had a bachelor's degree or higher. And the vertical axis is showing us the percentage of marriages ending in divorce. And the horizontal axis is showing us the years after marrying. So take a minute and look at this line graph. What is the picture telling you? Like, can you make any estimations from it? So the line graph shows us that it indicates that the longer lasting marriages occurred for those people with more education. Because you can see here, for instance, that this graph for the high school and no college increases much sharper. So if you just compare after 15 years, right, you can estimate approximately 40% of the marriages ended in divorce for people that had no college degree, compared to that's about 25% of couples that had a bachelor's degree or higher that ended in divorce. Okay, so here the longer lasting marriages occurred for those with a higher education. Now, does that mean that higher education will result in lower divorce rates? No, we can't say cause and effect here, but we can certainly see that there is a relationship between the highest degree that a couple has and the chances of them or probability of them, their relationship ending in divorce. Okay, there's factors that may affect that. Okay, so here's a new line graph, which we're going to look at in this example, and you're also going to use that same line graph to answer the questions below on your own. Okay, so the line graph shown to the right shows the percentage of U.S. college students who smoked from 1982 all the way through 2020. Okay, and you can probably see some trends here, you know, that there, for whatever reason, the percentage of college students that smoked decreased from the years 1982 to 1990. Then there was a sharp increase and then a gradual decrease from 1998 through 2020. So, you know, maybe people are realizing that it's not healthy for you. There may have been more advertising out there to kind of help people, you know, realize that it's not a good thing to do. There were also different, you know, in elementary school and middle school, they had different, you know, programs that would talk to students about the dangers of smoking. So those may be some reasons that we see the decrease there. Not sure why there's an increase in those years though. So we want to find an estimate for the percentage of college students who smoke cigarettes in 2010. So again, we need to estimate, right? So there's a reasons we're estimating. You know, we don't know exactly where 6% or 7% is here. We can assume 6 is in the middle, but where's 7 or where's 5, right? We also have to be careful with the years because it's not showing every year. Here we know that these are every 4, and the way I know that is because there's an 8-year gap. 1990 minus 1982 gives me 8, and I'm going to divide by 2 because there's 2 spaces there. So 8 divided by 2 is 4. So that tells me that this is 4 years past 1982, which would be 1986, right? Plus 4 is 1990, plus 4 is 1994, etc. So when I'm looking for 2010, I know it's here because 6 plus 4 is 10. Okay, so if I want to estimate the percentage of students who smoke cigarettes in 2010, I need to go here, and then I'm going to come across and look, and I can probably say it looks like it's about halfway between the square. So halfway between 16 and 20 would be about 18. So we can say that approximately 18% of college students smoked cigarettes in 2010. In which 4-year period did the percentage of college students who smoke cigarettes decrease at the greatest rate? So the greatest rate, if I'm looking here, I'm looking for the piece of the graph that has the highest slope, right? Or the steepest slope. So if you compare these in segments, right? Anywhere it's decreasing, like here it's decreasing, here it's decreasing, here it's decreasing, and there. Also here, right? And in here. Where is it the steepest though? It's in between these 2 years. So that would be from 2002 to 2006. In which year did 30% of college students smoke cigarettes? So now I have to look at the vertical axis, and we know 30 is going to fall between 28 and 32%, right? So if I go across now to where I hit the graph at right about 1998. So that's right where it's approximately 30% of students smoke cigarettes. Now I'd like you to use that same graph and answer the questions A through D below, and then you can unpause the video when you're ready to review. Okay, so in A, we need to find an estimate for the percentage of college students who smoked cigarettes in 1986. Okay, so I know that 1986, as I pointed out before, is right here. And if I go up where I hit the graph, it's about, we can say 22%. It looks like it's close to 21. Again, not certain. It could be 21.95% for all we know. It's just graphed in whole numbers, though, to make it easier to look at the graph. In which 4-year period did the percentage of college students who smoke cigarettes increase at the greatest rate? So here we're looking for the sharpest slope in the positive direction. Okay, so the steepest here. So where is it increasing? It's increasing here, and that's it. So where is it steeper? It's steeper from here to here. So this is 1994 through 1998. In which years corresponding to a tick mark on the horizontal axis did 24% of college students smoke cigarettes? So 24%. So here's your 24%, and we can already see that 1982 is 1 year that happens. But if I go across, I can also see that in 1994, 24% smoked. So we have 2 answers here, 1982 and 1994. And last but not least, in which year did the least percentage of college students smoke cigarettes, and what percentage of students smoked in that year? So least percentage of college students smoked cigarettes. And that would be in 2020 because that's the lowest on the graph, right? And we can see that it's about 8%. And for all we know, hopefully it's still decreasing. But it might be interesting for some of you to look up to see like what is the trend, what happened after 2020. Did college students increase again? Is it still in a decreasing trend? And if so, what percentage of college students are still smoking? And that's the end of this video. The next video that we'll get into will be all about solving word problems, the various techniques we can use. Specifically, we're going to look at Polya's method. So stay tuned for that. Hope you all enjoy your day, and please let me know if you have any questions.